So before you watch this video, hopefully you have already watched the video on the proof of this theorem. It's a pretty short theorem. It's a lot shorter proof than the proof that we went through to prove the first fundamental theorem, or the first part. But please watch that first. One thing I want to mention that can help this theorem be a little bit more accessible that was not in the video is if you think about what we know about antiderivative functions, we know that an antiderivative function has a plus c at the end, but these don't have any plus c's in them. And one way to help that sort of make sense is if you think about an antiderivative function of lowercase f of x, okay, that antiderivative is going to be capital F of x, which is going to be something plus c. And if we're evaluating an antiderivative function at two different points and subtracting them, we're going to have capital F of b is going to be something in terms of b plus c, and then minus the same thing with an a. I'll just draw that below. Okay, and then plus c, and we're going to take all of this and we're going to subtract all of this, and c is the same thing for a specific function. So c does represent any constant, but in the context of a single f of x function here, c is going to be the same. So when you subtract those, they cancel out. So basically, when we do a definite integral, when we evaluate that with the second fundamental theorem, we do not need to put a plus c anywhere because those plus c's cancel out anyway. Okay. All right. So I'm going to go through a couple examples here. I would encourage you to, at least after the first one, stop the video, pause it, and try and do them on your own, and then see how you do. Okay. All right. So for this first one, we have the definite integral from 1 to 3 of x squared plus 1 dx. From the second fundamental theorem, we know that we can evaluate this definite integral rather than doing the limit as n approaches infinity of the sum from I equals 1 to n of f of xi bar times delta xi. Instead of using the definition of the definite integral, we can instead find the antiderivative, plug in these two limits, and subtract. That's capital F of b minus capital F of a. So also please pay attention to the notation of how we do this, okay? So this is what it looks like. First, we find the antiderivative function. So here we're just using the power rule for integrals. So we add 1 to the exponent, which is x cubed, and then we're dividing by that new exponent, plus 1x. Again, we do not need a plus c right here. Okay, so now here is the notation that says we're evaluating this over the interval from 1 to 3. We're going to put either a straight line or kind of the right side of a bracket. You could put the left side on here as well. And if I were doing an expression that had two of them, I would use both sides of the grouping symbols. But really, notation-wise, it's totally fine just to put the right side, okay? And then I copy the limits again. So except I'll use the number. All right, so 1 and 3. So I rewrite my limits here, okay? And then I put an equal sign. So this is saying the expression 1/3 x cubed plus x evaluated on the interval from 1 to 3. All right, and then I take 3 and I plug that into the function, and I'll use parentheses here to group those together. So 1/3 times 3 cubed, which is 27, plus 3, okay, minus, so that's the capital F of b part. Go ahead and label this capital F of b, minus, now we plug in 1. So that's going to be 1/3 times 1 plus 1, okay? And then we do a little bit of arithmetic, and that's our answer. So this is going to be 9 plus 3 is 12, minus 1/3 plus 1 is 4/3. 4/3, okay? So that's 36/3 minus 4/3 is 32/3, okay? All right, for this next example, we have the definite integral from pi to 0 of sine x dx. Hopefully the first thing you noticed is that we need to have the 0 down here and the pi up here. So to switch those, remember we can put a negative in front and flip those upside down. Okay, so I'm going to write this as the opposite of the integral from 0 to pi of sine x dx. I've not yet evaluated the definite integral, so the integral symbol is still there. Okay, so now the antiderivative of sine, okay, the antiderivative of sine, well, the derivative of cosine is negative sine. We actually already have a negative here, so you could move that in, or if you want to think about it in a separate step, we're multiplying by -1 on the inside, -1 on the outside, which makes that a positive. So then we have the antiderivative of negative sine x, which is cosine x, and then that is evaluated from 0 to pi. Remember the lower number on the bottom, upper number on top, okay? And then equals, and now we plug those in. So it's going to be cosine of pi minus cosine of 0. Cosine of pi is -1 minus cosine of 0 is +1, so that's a -2. Okay, and this one we can think about whether or not it makes sense for that to be negative if we think about the function. Okay, so the graph of sine x looks like this. Okay, so from 0 to pi, we're talking about this region right here. But remember, this integral was from pi to 0, meaning we were accumulating from right to left. So because we're going from right to left, we would have the opposite of that actual area. Okay? And that might be something to remember just to kind of tuck away for later. The integral of one hump under a normal sine or a cosine curve, or the area of one of those is going to be 1 or -1, depending on which direction you go and whether you're above, 2 or -2, depending on whether you're above or below the x-axis. Okay? All right, now we are going to get a little more complicated here. We are going to have a lot of functions that involve compositions, okay? And we know that we can do U substitution. We've already looked at how U substitution works, but the thing is, when we have a definite integral, then we need to substitute the limits to be in terms of U as well. So it's actually going to be a little bit more work on the front end, but it's going to make the integral, or evaluating the integral, easier on the other end. Okay, so I'll show you what I mean here. I've got x squared on the numerator, and I've got root x cubed plus 1. Not only does this have a higher degree, but it's also part of the inside of another function. So my u is going to be x cubed plus 1. Okay, that means that du is the derivative of this, which is 3x squared plus 0, and then dx, okay? Now, do I have 3x squared dx? No, I do not. I just have x squared dx. So I'm multiplying by 3 on the inside, 1/3 on the outside, and now this is exactly equal to du. This part is u to the -1/2. Now, we need to change the limits as well. So we are going to take 0 and 2 and plug them into our function or our expression u. So u of 0 is 0 cubed plus 1. So this limit is going to become a 1. And then u of 2 is 8 plus 1, so 9. Okay, so this becomes 1/3 times the integral from 1 to 9 of u to the negative, just a second. U to the -1/2 du. Okay? Now, here's the thing. When I do my antiderivative in terms of u, I am not going to go back in terms of x. Also, these limits have to be in terms of u. If I have a 0 and a 2 there, then those would not be equivalent expressions. Okay? All right, so then we've got 1/3 times antiderivative of that, add 1 to the exponent, divide by the new exponent, so that's 1 over 1/2 is a 2. And we are evaluating from 1 to 9. So we've got 2/3 times, and this is a coefficient that applies to the whole function. So if you want to factor that to the front, you can. You don't have to. Okay, I'm going to go ahead and do that. So I have 2/3 times 9 to the 1/2, which is 3, minus 1 to the 1/2, which is 1. Oh my goodness. Pen's going crazy. Okay, so we have 2/3 times 3 minus 1, which is 2, which is 4/3. I think my battery's dying. Okay, let's do another one with the substitution. Again, we've got two factors. One of them is a composition, so we pick the inside of that to be u. Okay, so u equals x squared plus 1. du is the derivative of the, x squared plus x. du is the derivative of that. 2x plus 1 times the quantity dx. I do have a 2x plus 1 dx, so all of that gets used up. So I don't need to manipulate the coefficient. So this is u to the 1/2 du, but remember we need to change the limits. So u of 0 is equal to 0 plus 0 is still 0. U of 4, 4 squared plus 4 is 20. So our new limits are from 0 to 20. Okay? I don't know where that went. I don't know what's going on. Okay. And then our antiderivative of that is going to be 2/3 u to the 3/2 from 0 to 20. Sorry, I'm sure that's distracting because I don't know what's going on with it. Okay, 2/3, and then I've got 20 to the 3/2. Oh my goodness, let's get through this problem. Minus 0, so I'm just going to leave it like that. And I'm going to pause here and try and figure out what's wrong with my battery. Okay, let's see if we can get through this last one before the battery completely dies. All right, so again, I'm looking at a composition of functions, this time in the denominator. So I'm going to make that u. So u equals x squared plus, nope, gonna be sucky again, plus 2 x plus 6. Okay, so du equals the quantity 2x plus 2 dx. I have x plus 1 dx, so I need to multiply by 2 on the inside, 1/2 on the outside, so this matches du now. Okay, putting the limits in terms of u, I have u of 0 equals 6. U of 1 equals 1 plus 2 is 3 plus 6 is 9. So this is now 1/2 times the integral of u to the -2nd du, and the new limits are from 6 to 9. Okay, by the way, if something about your u makes the bottom number bigger than the top number, after you write your new limits, then put a negative in front and flip them upside down. Don't just automatically flip them, okay? You need that negative still. All right, so then we have 1/2 times, and then that's going to be u to the -1st, and 1 over 1 is just 1, so we don't need that here. All right, and then, oh, I'm sorry, -1. We do need a -1, okay? And then we're evaluating from 6 to 9. So we have -1/2 times 1/9 minus 1/6, which is -1/2 times common denominator. This would be 2 over 18 minus 3 over 18, which is -1 over 18. So we get +1 over 36.